I'm going to present argumentation semantics on the claim-centric view, where we basically investigate central properties of two different versions or ways to lift argument to incorporate claims in argumentation semantics. So I'm Rapberger, and this is joint work with Wolfgang Dvořák and Stefan. So here we have a prototypical example of an argumentation process where one starts from a knowledge base, constructs arguments where each argument has a distinct claim, a conclusion, and identifies conflicts. And then in the next step, one abstracts away from the internal structure and resolves conflicts. So one is interested in sets of jointly acceptable arguments. And this all works fine if one is interested in the argument-based outcome, but things start to look a little bit different if one is instead interested in a conclusion-based evaluation. So basically here we have different concepts of evaluation when focusing on claims in the argumentation process. So let me explain what I mean with this. So here we have the example from the slide before, the argumentation framework, the abstract argumentation framework, which is additionally labeled with the claims of the arguments. And we're interested in preferred semantics, where a set is preferred if it is a subset maximal admissible set, so a set which defends itself and is conflict-free. So here we have the list of self-defending and conflict-free, so admissible sets. So for example, the set C1, C2 here is in fact conflict-free and defends itself against each attack. Now we have the list in terms of claims. So here we simply inspected the claims of the argument in order to get the admissible claim sets. And here one thing is interesting, we see that one claim set might have different realizations. So here the admissible claim set C can be realized by C1, C2, but also by the respective singletons. And so now we are interested in the, so basically now we have two different approaches for claim-based preferred semantics. So the one approach simply looks at the first list and maximizes over this first list of arguments of admissible sets and interprets the outcome in terms of claims. So we have argument-based maximization, which yields the claim sets AC, C, and BC. One could also directly go to the admissible claim sets and maximize this list. So then we get the set AC, so the claim sets AC and BC. So here we have two different approaches, where the argument-based maximization is used in many argumentation procedures, but on the other hand, claim-based maximization is used in related formalisms where one aims to maximize over accepted conclusions. So for example, in logic-based, logic programming instantiations. So we have two different approaches with both having their advantages and justifications. But this is interestingly, we see that we can't capture either one entirely with the other one. So yeah, we investigate these differences by using claim-augmented argumentation framework, where a claim-augmented argumentation framework, or CAF for short, generalizes an abstract argumentation framework by assigning claims to arguments. So we have a set of arguments and as usual an attack relation, and in addition a function which assigns claims to arguments. We furthermore call a CAF well-formed if arguments with the same claim attack the same arguments. So and what we did is we studied claim-based argumentation semantics with respect to these two different approaches. So the argument-based or inherited approach and the conclusion-dependent, the claim-level approach. We consider in this work preferred and naive semantics. So these are the semantics which maximize, but also the range-based semantics, so stable, semi-stable, and stage semantics, where range-based semantics take also defeat into account. Now, we provide an in-depth comparison of these two different approaches, the inherited and the claim-level approach, in terms of subset maximality of the outcome, so I-maximality, relation between the semantics, but also relations of well-formed CAFs and SETAFs, and expressiveness of semantics. So yeah, this is a lot to talk about. So I will focus in this talk mostly on preferred, but also on stable semantics in CAFs and in well-formed CAFs. So we defined inherited semantics by interpreting the argumentation, so dung-IF extensions in terms of the claims. So we already saw this example, the I preferred, so inherited preferred claim set of this example were C, AC, and BC. We also want to consider stable semantics, so set is stable if it is conflict-free and attacks all other arguments. This yields here the unique stable extension with the arguments B1 and C2, so this yields the I stable claim set BC. Yeah, for claim level semantics, the general idea is to perform certain steps in the evaluation directly on claim level. So we already saw claim set maximization when we talked about claim level preferred semantics, but we also want to consider range-based semantics. So we also need a concept for claim defeat. So CL preferred claim sets were AC and BC. And yeah, in order to introduce a claim level variant of stable semantics, I will first have to speak about claim defeat. And yeah, we say a set of arguments defeats a claim if each occurrence of this claim is attacked. So let me give you an example here. The argument A2 attacks the arguments B1 and C2, but it defeats only the claim B since not each occurrence of the claim C is attacked. We say a set of claims is CLCF stable, so CF standing for conflict-free, if there's a conflict-free set of arguments which realizes this claim set, so claim equals S, and E defeats all claims, all remaining claims. So if we now consider this semantics on the example cuff, we get that we have the CF stable extension BC. So this was also I stable, if you remember. But in addition, we also get the CL stable claim set AC realized by this set of arguments A2, C1, since as we had before, the argument A2 defeats the claim B, and that's all what we need. So we don't care about all the other arguments because they're all anyway labeled with claims which are present in the considered claim set. Yeah. So in general, we see that we have that each CL preferred claim set is in fact I preferred, while for stable semantics, the subset relation is the other way around. So we have each I stable extension claim set is CL stable. Now for well-formed cuff, we have in fact that the inherited and claim label variants of stable and preferred semantics coincide. So this does not hold in general for especially actually it does just hold for stable and preferred semantics. So for the other semantics under consideration, we have that they do not collapse in well-formed cuffs. So here, let me give an example for naive semantics, which are, so a set is naive if it is a subset maximal conflict-free set. And here we have a well-formed cuff. And if we now consider the I-naive semantics in this well-formed cuff, we get the claim sets A realized by A1, A2, AC, and BC. So this is not I-maximal. While on the other hand, if we perform maximization directly on the conflict-free claim sets, we get as outcome AC, BC. So here we have an example of a well-formed cuff, but the naive semantics two variants of naive semantics still yield a different outcome. So this is two graphics show our overview of the relations between the semantics, the left one for general cuffs and the right one for well-formed cuffs. So here an arrow indicates subset relation. And yeah, in general, we see that for well-formed cuffs, the semantics behave in general a little bit more tame, so to say. So we have that the preferred versions collapse, the stable versions collapse. We also considered an admissible-based stable version, but yeah. And also we have that naive semantics, or CL naive semantics becomes part of these subset chains here. And still we have that even in well-formed cuffs, the different variants of semi-stable and stage semantics might yield a different outcome. So here we see the inherent difference of these two different versions with respect to the semantics. Okay, now I'm coming to the relation to SETAFs. So in which way are cuffs now related to SETAFs, where SETAFs is an extension of Dung argumentation frameworks where one allows for collective attacks. So basically, in well-formed cuffs, it is in fact possible to merge arguments having the same claim as we showed in recent work. So we have here, for example, the two arguments having the claim A, which can be merged in the corresponding SETAF. So the basic idea is that a set of claims successfully attacks another claim if each occurrence of these arguments having this claim is attacked. So here we have all claims with, so the claims with B attack the argument A1, and claims with arguments with claim C attack the argument A2. So jointly they attack the all arguments having claim A. And yeah, in fact, the translation preserves claim level semantics. So the reason here is that maximization of arguments in the SETAF corresponds to claim set maximization. Okay, now I'm coming to expressiveness. So we are also investigated the expressiveness of the semantics. So the question here is how expressive are the semantics in terms of which outcome can they realize? So for example, given a sets of claims, an extension set, for example, the set here containing the claim sets AB, AC, and BC, and a particular semantics, is it possible to realize this extension set under the semantics? So here in the example is S realizable under CL preferred semantics in a cuff or in a well-formed cuff. And well, yes, it is possible, and the construction works as follows. So first we introduce, for each claim set in the extension set, we introduce arguments where, which are labeled with the corresponding claim. So here we introduce A1, B1, A2, C2, and B3, C3 for each set of this in this set. And yeah, they're all labeled with the corresponding claim. And then we introduce the attack relation by saying that for each set, for the corresponding arguments are attacked by all arguments labeled with a claim which is not part of the set. So here these arguments A1 and B1 correspond to the set AB, and they are attacked by the arguments labeled with claim C. So this in fact realizes the example extension set, and in fact it works for all I-maximal sets which are non-empty. So we showed that each I-maximal set which is non-empty can be realized under CL preferred semantics. For I-preferred semantics, the situation looks a little bit different. So basically here, almost everything can be realizable if it is non-empty and if it either exclusively contains the empty set or does not contain the empty set. Yeah, to the overview of the results. So these are basically the two categories which are sufficient to characterize the expressiveness of the semantics. So for general cuffs, just CL preferred and CL naive semantics can be characterized by I-maximality, while the rest is way more expressive. And for well-formed cuffs, the picture looks a little bit different. So here, basically, almost all semantics under consideration can be characterized by I-maximality. So if you take a closer look, you might see that there is one semantics missing, namely I-naive semantics. And yeah, the reason is we don't have a precise characterization for I-naive semantics for well-formed cuffs yet. Yeah, so to sum up, we provided here an in-depth comparison of inherited or argument-based semantics and claim-level semantics. So for naive and preferred semantics, we had that the claim-level semantics yield an I-maximal outcome, which is not the case for inherited semantics. They potentially violate I-maximality. Coming to range-based semantics, so for stable, semi-stable, and stage semantics, we saw that there are somehow similar results concerning I-maximality and expressiveness, although we had that for well-formed cuffs, even for well-formed cuffs, these two variants are incomparable. And also we have that preferred and stable semantics behave kind of nice, so they coincide for well-formed cuffs. So for future and ongoing work, we are of course interested in the computational complexity of the semantics and in the expressiveness of I-naive, but also conflict-free, admissible, and complete semantics. And we want to connect our findings to structured argumentation formalisms. So for example, ABBA and ASPIC+. Yeah, thanks for your attention. I'm looking forward to your questions.